Hi, everyone. Welcome back to the videos. In this set of videos, we're calculating the magnetic field for a very classic problem, which is an infinite sheet of current where the current is moving in just one direction. In the previous video, I showed you why this rectangular loop is an acceptable Amperian loop, and we looked at how the top and the bottom of this loop contribute with a constant magnetic field, whereas the parts of the loop in the vertical directions don't contribute any magnetic field at all. In this video, we're going to calculate the current through the Amperian loop. And then we're also going to calculate the integral around the loop. And we're going to come up with a final expression for the magnetic field. So remember, right, we are going to try to calculate the current through this loop because we're trying to solve this equation where we have a left-hand side and the right-hand side. And on the right-hand side, we can see that the total current is on the right-hand side. And so that's what part 5 is going to be showing. So if we consider the length of our Amperian loop to be length L, and we have a surface current, which is coming out of the page as x hat JS, then we know that this surface current, right, is in amps per meter. And so the total current in this case can easily be found as the surface current multiplied by the length. Okay, and so this is just going to give us JS times L. And we can see, right, that amps per meter multiplied by meters, right, the final result of this is in just amps. So now we have a result for the right-hand side of the equation. So this JS L must be equal to the total amount of current, which must be equal to the magnetic field dotted with this path, where the path goes all the way around our Amperian loop. So now let's look at part 6, where we should calculate the other side of the equation. So this is the left-hand side of the original equation that we are looking at. Now, to calculate this, right, we have 4 different paths. And so like other integrals, we can break this up. Now, let's start by looking at this and breaking this into each corner into junctions where we can make the path. And let's integrate from 1 to 4. And let's do that. Let's make the direction of our integral go this way based on the right-hand rule. So if we put up our right hand and we point our fingers in the direction of this path, we can see that the thumb is in the positive X direction out of the page. Our thumb is in the same direction that the current is. So we can write this up as 4 different integrals. Okay, so we have 4 different integrals. So from 1 to 2, 2 to 3, 3 to 4, and from 4 to 1. And recall, right, some of these integrals are not actually going to contribute to our final result. And that's going to be these vertical integrals. These, in these integrals, right, these don't add to our calculation. Okay, so this one is equal to 0, and this one is also equal to 0. So this leaves us with a simplified expression with just 2 of the 4 integrals. So in this first one, let's integrate this. And on the top, remember, we had the magnetic field is pointed in this direction. And you can go back to the first video and see this. So on the top, the magnetic field is pointed to the left in the minus y direction, and in the bottom, it's pointed to the right in the plus y direction. And you can find that using the right-hand rule and modeling this sheet of current as an infinite number of small wires side by side with the wire current traveling in the plus x direction, which is out of the page towards us. So on the top, we have a constant in the minus y direction dotted with dl, which is y dy. And our limits here, we're going to say that the length of our Amperian loop, right, it starts here at 0 and it goes all the way up to length L. So we're going to need to integrate from 1 to 2, so from length L to 0. And then for the second one, we're going to come down here from 3 to 4. And in the bottom, the magnetic field is in that plus y direction, right? So again, you can use your right hand rule, put your right hand up, point your thumb in the direction of the current, and you'll see that your fingers are pointed in that positive y direction when you're underneath the sheet of current. And so we'll get these two integrals. Now, hy is a constant, right? We've determined that hy would be constant everywhere along this Amperian loop, which means that it's not a function of y. So these two integrals are going to reduce down to something fairly simple. And when you combine these, right, we see that the final result of this is going to be 2 HYL as the final result of these two integrals. Okay, this gives us the final result. And so this set of integrals, right, we just completed this side of the equation, where the right-hand side is equal to that total amount of current. So now we have the left-hand side and the right-hand side. So based on this, we can arrive at a final expression for the magnetic field that we solved using Ampere's law. So from problem 5, or part 5 of this, we arrived at this as the total current as JS L. And again, this is just a magnitude. And then in part 6, we found that the left-hand side, this closed path integral, is 2 HYL. And so if we solve this, we see that this constant must be based on the surface current divided by 2, where the length of our Amperian loop path does not actually matter at all. And going way back to this early equation where we said that we would have a constant magnetic field above and below, we can now finally write this as the total magnetic field when we are above the infinite plane is in that minus direction, and when it's below, it's in the positive direction. And by following this set of instructions, or this cookbook, as you might call it, right, we have arrived at a total expression for the magnetic field in the two regions that we said we were interested in part 3, so above and below. So this is the final answer. One thing that you should know is, interestingly enough, right? This does not actually depend on at all on how far away you are from the sheet of current. It only depends on the current strength. And we can see that it's symmetric above and below the plane, with the symmetry such that above the plane, the field is in that minus y direction, but below the plane, it is in the positive y direction. So thank you for watching this, and I hope to see you in the next videos. Goodbye.